Well, good afternoon, everybody. We're going to be talking about a new property called temperature, which I'm sure we're all very familiar with. Anyhow, if you will, go ahead and get out your general physics instrumentation control chapter number 2, talking about temperature sensors and detectors. And that is going to be with the green banner at the top of your page. So go ahead and get that out. Also, go ahead and get your highlighters out. I have a lot of information inside this chapter that I need you to highlight. Also, at the end, during this time period, we're going to be having a quiz online for you this week. I know you're all excited about that. And look forward to learning the new things about temperature sensors and detectors, which are pretty neat overall. So I'm going to continue moving up, highlighters up. Going to pass the table of contents, get over here to your objectives. There's a few things in your objectives I want you to go ahead and highlight. Number one, this is it. State the 3 basic functions of temperature detectors. That's a pretty good one. 3 basic functions of temperature detectors. Second thing is, what are the 2 environmental concerns that affect the accuracy and reliability of the temperature detection instrumentation? Which is pretty interesting. What 2 environmental concerns affect the accuracy and reliability of the temperature detection instrumentation? And also I want to point out, do you remember what the term accuracy means? What is accuracy? All right, I'm going to keep on moving on. We're going to talk about what's called a thing called a thermocouple, which is a pretty interesting device. We use a lot of those at the nuclear power plant. In addition to the RTDs, which are called resistance temperature detectors, RTD. So did everyone get that written down? State 3 basic functions of a temperature detector, 2 environmental concerns, the thermocouple, the RTD, and then after that we're going to talk about all these miscellaneous objective items as we go, including the temperature circuitry that we're going to use for RTDs and thermocouples, in addition to the block diagrams at the very end. Okay, so here we go. Functions, uses of temperature sensors and detectors, and I guess you all are very familiar with the number 1 temperature sensor, which is the thermometer. And so we're going to begin with definition of temperature. Remember, temperature is a measure of the kinetic energy of molecules of a material. So I hope that everyone remembers the definition for temperature, measure of the kinetic energy, or you could say the measure of the heat and transfer, which is energy and transfer, which is heat. If you remember that from the last chapter. Okay, we're going to keep on going. Temperature is one of the most parameters of a material. Is one of the most important parts of the material, especially a nuclear power plant. That's all we're working with is a lot is temperature and pressure, and so we need to have accurate instrumentation. It's your responsibility as INC techs that you are going to be calibrating these temperature sensors. I'm going to talk to you a little bit later on about the different loops. When coming out of the reactor, we have 3 thermocouples that are detecting temperature coming out of the reactor, and it's really strange how each one of those I got a story behind that. I'll tell you that a little bit later. All right, let's keep on going. We have the not only the thermometers, but we also have what's called the resistance temperature detector. That's talked about the very last part of the chapter, and then we're going to talk about thermocouples. All right, so here are the different things that we are going to be very temperature sensitive, especially for the control room, is the reactor hot and cold leg temperatures. Second thing is the pressurizer temperature. What is that? And purification demineralization inlet temperature. That's very important because we have too high of a temperature within our demins, we can actually melt the material, the resin beds, inside the demineralizers, and then no longer be able to filter our water properly. So that's a big deal there. How about this one? Cooling water to form various components. Cooling water, there's a whole system that we use called CCW, component cooling water, in the reactor in the aux building area, which supplies cooling water to a number of different components, not just the pumps, but we actually have heat exchangers that pull that heat out and also cool down things like reactive coolant pumps, charging pumps, RHR pumps. All those things we'll be learning in the Nuke 120 class. All right, and then also the secondary feed temperatures. Very important that we know how much temperature we're getting out of our steam, and then what the temperature is of the water in the hot well, the condenser, as we bring it back to the steam generators. So go ahead and highlight those 4 bullets, 5 bullets, excuse me. Reactor hot and cold temperature, temperature legs, pressurized temperature. The DMINs in the chemistry department, the cooling water, or for cooling components, also known as CCW, component cooling water, and then secondary feed temperature. And there's a number of different places that we measure temperature over on the secondary side, as you can imagine. Steam coming into the high pressure turbine, water that's being condensed in the condenser, as the water goes back through the feed water heaters, all the way up to the steam generator feed pump, back into the steam generator. Each one of those temperatures need to be monitored in addition to each side of each heat exchanger as it goes. All right, so here we get back to what I had spoken to you earlier about, was the 3 functions of temperature detectors. 3 functions. Here they are. Number 1, indication, indicate what kind of temperature you have. Number 2, alarm, and number 3, control. As you can imagine, the detectors are going to indicate what temperature it is, or whatever they're measuring. Number 2, there may be alarm set for alarm high or alarm low, and that will probably be in the control room most of the times. And secondly, some kind of circuitry or some kind of device that's going to control the temperature based on pump speed. Maybe it's less pump speed, maybe it's more steam pressure, whatever it might be. Those different sensors are going to function, indication, alarm, and control. Make sure you have those highlighted, okay? All right, moving on. Page 2. Here we go. They're talking about some of the detector problems. They actually get in the further part of the chapter, we get into more detailed issues about detector problems. These are pretty much in a nutshell. Speaking about RTDs, which is resistive temperature detectors. They talk about having an additional spare sensor in the system. At the nuclear plant, we have a lot of redundancy, so we may not necessarily have one temperature detector in a certain system or a certain location. We may have 1, we may have 2, we actually may have 3, depending on what the criticality is of that particular system and how important it is to protecting the general health and safety of the general public. All right, the other one is called a pyrometer, which is actually a portable thermocouple. A lot of the SOs carry those around, and they check a lot of things like pumps, pump casings, electrical drives, the motors, motor casings, and they can just actually press this particular device up to the casing and be able to measure the temperature. Much easier than probably what you might think of as take your little thermometer out of your pocket and stick the bulb up to it and see what the temperature is. I would not think that would be a great way of determining temperature. However, these pyrometers, the portable thermocouples, work really great, and they're very, very fast. And you got to remember, it's very hot. That stuff is hot in the nuclear plant, and so those SOs, they're great about, if I can get the temperature and I'm on my way back to the shop so I can drink my Coca-Cola and eat my crackers, they are excited about that. Okay, the other thing is malfunction of the circuitry that is controlling the detector. And if you have a malfunction of the circuitry, obviously your detector is not going to operate any longer. Now, there was 2 environmental concerns that I talked about earlier that I wanted you to pay attention. Here they are. Environmental concerns. One is ambient temperature variations can affect the reliability of your temperature detection instrumentation. I'll give you an example. Number 1, seasonal. If it's hot in the summer, you're going to have a different ambient temperature within the turbine building and or the auxiliary building or the containment building. So versus the winter when it's going to be cooler. Although it is very warm in all of those locations, the turbine building is going to be a little bit cooler than it would be in the summer. Aux building and the containment building, all the same situation. You may have a variance in temperature. So if that's the case, then you may have, because of that variation in temperature, you may have some components within your temperature detection equipment that are sensitive to that ambient temperature and therefore give you a inaccurate reading just based on the location of where that thermometer is located at, or excuse me, temperature detection equipment. You couldn't rely on a thermometer because obviously a thermometer is going to be measuring ambient temperature just by carrying it around. So other instrumentations can be dependent and or varied by this ambient temperature. The second thing is humidity. And because of humidity, if we have high humidity, you know that a lot of moisture collects on certain things. That moisture that collects on, say, hot steel or casings of the equipment, so on and so forth, will condense. That moisture will drip down, causing a temperature deviation between the outside, whatever it's measuring, to the chassis or the output or the housing of the detector itself. In addition to that, you could also get moisture inside the detector and therefore actually short it out and cause possible corrosion and detriment to the detector. So let's review two environmental considerations. Is number one, ambient temperature, depending on where it's located in the plant, and number two, humidity due to moisture accumulation and or corrosion. And here it is. Moisture can cause short circuits, grounds, and corrosion. All right, did everyone get that highlighted? That's just page 2. I tell you, we have a lot of stuff to cover, and I know you're really excited about this, so we're going to move on to our simple temperature measurement devices. And I bet you all know what that is. That is the liquid and gas thermometer. Well, that's the same thing as saying, well, those are the same thermometers that you use in chemistry and they use in the medical facilities. It's got the glass around with the mercury inside. And how those work is due to an increase in temperature causes an increase of the volume. The liquid that's inside the thermometer expands. And so that measurement of expansion right here, the measurement of expansion of that particular material is converted into an indication of temperature, which is, as you know, a sight glass type indication where you read it on a scale on the outside of the glass itself. Also, other types of measurement could possibly be a pressure change and or electrical resistance based on material changes with temperature. We're going to talk about electrical resistance on the RTDs and the thermocouples. Have everything to do with electrical resistance. Measurement of expansion is going to be your thermometers, your glass tube thermometers. The measurement of pressure change is going to be into a different device called a Bourdon tube, which is very interesting. Chapter 3 talks all about it. We'll be able to do that next week when I get to see you in person, which will be a whole different aspect. Here we go. Liquid and glass thermometers is one of the simplest temperature measuring devices. That is our thermometer. Is usually filled with mercury. I've never seen one made out of alcohol, but mercury is the one I'm most familiar with, and I'm sure you guys are too. They have liquid thermometers that can range all the way from a negative 328 degrees. Wow, that's cold. I mean, that's real cold. Because remember in Rankine, what is Rankine? 0 degrees Rankine is approximately 460 degrees Fahrenheit, so that's pretty low. And then going up to 1150 degrees Fahrenheit, they make thermometers that will actually operate in those temperature ranges. The one of the second type of fluid system thermometers would be the Bourdon tube, along with some kind of capillary tube that runs from a distance, and it goes from a further part. That's because you may not be able to measure the temperature right there next to it. Could be radiological responses, could be a health hazard, might be too hot to approach, and so we need a distance. So we use these fluid system thermometers to measure temperature in a distance. Okay, here we go. This is some fun stuff. We got the Bourdon tube spiral temperature indicator. This is this guy right here. I don't know if many of you have ever seen this or experienced one or taken one apart. We have a lot of these type detectors in the nuclear power plant, also in a lot of other plants. And how that works is there's a sensing bulb filled with a particular type of material. It could be mercury, it could be water, not necessarily water. It goes through a long capillary tube where it actually comes to the meter. So this capillary tube could actually be up to almost 40, 50 feet long, depending on where the sensing bulb is versus where the actual meter is. And so this is very important that we understand how this operates. The sensing bulb, obviously, in this particular case, is a closed system, so it's an increase of pressure. That increase of pressure is transmitted to this bored-on spiral tube. And as that pressure is increased, the spiral either expands, which moves backwards, or it moves forwards, depending on what the sensing bulb is sensing. And then from there, it's got a little needle attached to it, and it can read either cooler or hotter, depending on which way the needle moves, based on this capillary tube and sensing bulb. If you remember, I don't know if many of you are familiar with your air conditioning systems, but most all heat pumps and general air conditioning systems have a sensing bulb that's attached to a coil of wire, and then has a capillary tube attached to it, which tells your electronic device whether to turn on your air conditioner or turn it off. Not like the thermostat, but it has to do with maintaining or controlling the motor inside your air conditioner. This is one example of this type of system using a system bulb. All right, moving along, we're going to go to the bimetallic strip thermometer. This is a really interesting device. The bimetallic strip thermometer uses a simple rugged device for monitoring temperatures, blah, blah, blah. This is what's fascinating about it. It has two types of metal. These two strips of metal are joined together, as you see alpha and bravo here. The two normal types of metals that are used for this type of device is aluminum, let me get that highlighted, and iron. And what it does is, as the temperature changes, these metals have different what's called up here coefficients of linear expansion. Coefficients of linear expansion. So that means even though the iron and the aluminum are at the exact same temperature, say like it's 100 degrees Fahrenheit, the aluminum is actually going to expand further than the iron. And since they are mounted together, the aluminum will either bend the iron one way or bend the iron the other way, depending upon what the temperature change is, which is pretty neat on how they do that. So here's the description. Go ahead and highlight this paragraph. It says both strips of the metal are joined. They will always be at the same temperature, obviously. If this Bravo is 100 degrees Fahrenheit and Alpha is 100 degrees Fahrenheit, they will be the same temperature. However, what changes here is that the length that they expand due to the temperature. That's what's the big deal about this. So that when the strip is heated, it will force to bend as shown above. Now, don't think this is a big, thick piece of iron. They are not. They're very, very thin, and that's why you can get this bending to occur in this type of detector. Now, remember, this detector requires that a known value, or what's called the coefficient of linear expansion, is known. And you must know that so you can have your circuitry connected to this, be able to determine what is hot or what your degree temperature change is, and so on and so forth. Let's just take a look at the coefficients of linear expansion. Let's go down here and look at iron just for a minute. Look there, it's 11 times 10 to the negative 6. Notice what units it's in. Got to pay attention to your units. Centimeters. 11 times 10 to the negative 6 centimeters are expanded for each degree centigrade. I would not know what kind of ruler we're going to use for that, but there's going to be, obviously, someone has figured that one out. And then notice over here, the aluminum is almost double. See that? It's almost double the linear thermal expansion. So it almost goes double the amount of the iron at per degree centigrade. So you can see where this guy would really, really bend pretty good based on the aluminum expansion. All right, so this gives an example down here, this picture 2-3 of the bimetallic thermometer. And what they do is they take the two metals, they join them together, and they put them in a little spiral. And as that aluminum gets longer, it causes the spiral to either contract or go backwards the other direction. It's not going to contract, expand. And when it expands, then it can move this needle, whether it's hot or cold, it's not necessarily going to be hot or cold. Dr. Seuss could tell you that, but they would have the temperature range specified on your needle, so you can determine what temperature is based on the temperature of the two dissimilar metals. So that is your bimetallic strip thermometer. All right, now we're going to move on to a different detector, and this is pretty interesting. It's called the thermocouple. The thermocouple is a device that converts the thermal energy directly into electrical energy. What is the name for that device? Tell me what that is. That is a transducer. How about that? Going directly from thermal energy to electrical energy. It's just like our pressure indicator at the bottom of our tank in our lab, our little lab equipment, where we have the pressure sensor changes it directly from pressure to electrical output. This guy, the thermocouple, will actually convert the thermal energy, or the temperature, the energy of the heat, directly into electrical energy. So that was a pretty interesting discovery. And let's look and see how a thermocouple is actually composed, and how in the world does that do that. Now, so I want you to notice first, thermocouples can be used to measure temperatures from sub-zero to over 300 degrees Fahrenheit. Now that's pretty good. Now in a nuclear plant, you know that our temperatures range from ambient, usually around 70 degrees Fahrenheit, all the way up to approximately 575 and or 582, which is tech spec on the pressurizer. So 3,000 degrees Fahrenheit is not something that we would definitely be measuring our water or piping in. However, if we did have a loca of some sort, then there would be a possibility that we could get radioactive temperatures in the reactor vessel exceeding 3,000 degrees Fahrenheit, which would be extremely scary. That's when you want to get in your truck and head for the gate. And do not drive towards Georgia, remember? That's the way the plume is moving. All right, here we go. A thermocouple is composed of two wires of dissimilar metals, very similar to the bimetal, but this is going to be creating a voltage instead. The wires are joined at one end, which is typically called the sensing junction or measuring junction. Now I want you to look down here at the picture where they have the two dissimilar metals. One's listed showing as a white arm or white branch, and then the other one's kind of grayed out. I don't know if you can see that well on the projector or not, but if you're looking at your text material, one is grayed and one is white. And then they coil them together, or join them together on one end. This is called the sensing junction right here. Go ahead and highlight that. And I want you also to notice that the sensing junction is going to be your hot side. Okay. Then they have the other side, which is going to be your voltage indicator. Notice it says a developed EMF, electromagnetic force, voltage, and it's considered your cold side. Is it actually cold? It's cooler than the junction side. Let's put it like that. It's not necessarily always cold, but it's cooler. All right, this side develops the voltage based on the expansion of the two wire branches. This side is actually going to be placed into your medium, whatever you're testing. In the nuclear plant, obviously, that's going to be water, but it could be a number of different things. It could be steel. How about in the steel plants for molten steel? It could be in any other type of plant environment where you're having to deal with something that's very, very, very hot and or very, very, very cold, like you would experience in a chemistry. All right, so as the temperature of the sensing junction is increased based on the properties of these two metals, there's an electromagnetic force that is developed between the two metals, which means a voltage, a potential difference. And that potential difference, that voltage, is measured by a voltmeter and then corresponds directly to the temperature of the particular medium you're measuring. So that's pretty cool. Now we don't have to do, this is a transducer, which goes from heat right to voltage. All right, now I want you to look at this. There are different types of metals that are used for the thermocouple. There it is on the other side. But before we move over to there, it talks about there's two dissimilar metals can be used for a thermocouple. However, here are some of the following requirements that must be met. Number one requirement, let's go ahead and highlight these bullets. Number one, the melting temperature of the metals must be greater than the highest temperature to be measured by the thermocouple. That's pretty self-explanatory. You wouldn't want to sit your thermocouple in a medium which melts it. Yeah. So, I don't know. Charlie Brown might not do this, but I don't know. You guys be smart in that. Number one, do not make your thermocouple melt in the medium you're recording. Number two, the voltage produced by the thermocouple must be large enough to measure. And you try to get to linearity or proportionality as much as possible by depending on which metals you're using in the thermocouple itself. Number three, you got to make sure that the thermocouple metal is not corrosive in the environment you're measuring. And that's a big deal in chemistry, but it also can be a big deal in the reactor coolant system because we use boron, and boron is a highly corrosive material, and we use that as a nuclear poison or radiation poison. We call it a poison because it reduces the fission process of the uranium and the neutrons. It's a neutron absorber. However, it's a very corrosive environment, and the thermocouples that we use in the reactor coolant system have to be to where they will not have an oxidizing or corroding property inside that area. The thermocouple must be easily economically made. Oh gosh, I don't even know why they put that in there. Everything at the nuclear plant is expensive. And the thermocouple metals selected must be easily attached to each other. That's a no-brainer because look back up here at your picture. Whoops, wrong way. Picture right here, you can actually see where you have to have them attached so you have a differential in temperature here so you can get a differential in your voltage there. Okay. Now, what kind of metal are we going to use for these thermocouples? Very interesting question. Number one metal, platinum. Platinum is one of the better metals that we can use for a thermocouple. And then there's other different metals that can be associated with that platinum. Obviously, they're showing iron, constantine, which is copper, and nickel. I don't know about the copper. That seems to be pretty corrosive. Chromium and nickel, which is not as corrosive, very stable metal, along with aluminum and nickel, common elements for the thermocouples. Okay, normally the platinum is used as one of the metal. Go ahead and highlight this. Normally platinum is used as one of the metal irons because the properties of platinum is very good for proportionality, and that's why we use platinum. And then also the other factor that you have to maintain is what is the thermoelectric difference. That is a nice fancy word for what is the voltage difference, thermoelectric difference between the two metals. The larger the difference between the metals makes a better thermocouple performance, and that's stated that because if you have a larger voltage between the two metals, it's going to be easier to measure than when you have something very, very small in between those. Okay, so that's our thermocouple, and here it's giving you a characteristic curve of platinum versus your voltage based on what kind of metals you're going to put with that platinum. Take a look at what some of them are, and notice that you have iron. Wow, what a change. Not very consistent in terms of voltage for iron. I'm going to scratch iron off. He's not very good. Let's take a look at Constantine. Remember, you come back up here. What is that stuff that was made out of? Here it is, copper and nickel. They throw the nickel in there to try to help in the corrosion of copper. Notice it's more of a logarithmic curve. So I wouldn't say that is as good as proportionality. More logarithmic. And then look at copper. Wow. Out of all of these lines that I see here, copper looks the most promising as your second metal with platinum. Number one, it has a better proportionality, a more linear curve, your y equals mx plus b. Number two, it has a greater difference in potential, goes from 0 almost up to 30 degrees centigrade based on that of the platinum down at the bottom. So you can tell where platinum and copper might be your main choices in your thermocouple material. All right, we have other materials that are used that aren't shown here, which is the nickel-nickel molybdenum. The nickel-nickel molybdenum is very, very good. It's more in your stainless steel. Very good for corrosion properties. And also, notice down here we have tungsten. Tungsten is used most of the time in very, very high temperatures. Look at this, up to 5,000 degrees Fahrenheit. So platinum and tungsten. Right over here gives you an idea of how a thermocouple is actually constructed inside its housing. Over here is going to be your sensing junction or your measuring junction. I want you to notice that in this text, the author has been swapping back and forth, saying this is your sensing junction. He also calls it the measuring junction. So I want you to make sure those two are equal. I don't know why he changes terminology, but sensing junction and measuring junction is the same location. It's the same thing. Then we have our two dissimilar metals, which are surrounded by magnesium oxide. Magnesium oxide does one of two things. Number one, here you go ahead and highlight that. Number one, it prevents vibration between the two little thin wires. And the second thing it helps enhance the heat transfer between the outside medium, which will be your Inconel sheath. Inconel, we use that in the reactor itself, and the surrounding thermocouple. Notice right here, and the measuring junction. There he is, swapping it again. Measuring junction, sensing junction, all the same thing. It's this guy right here. Measuring junction, sensing junction. Now he's going to be using another term called the reference junction. That's going to be here on the ends of your leads, which is connecting up to your circuitry and your voltmeter. So if you hear sensing junction, measuring junction, it's located here. And this is going to be your reference junction. Make sure you know the difference between those two. Okay, this one goes on to show you a typical diagram of what the thermocouple may look like in real life. It's got some kind of set screw right here to connect this up, along with the electronics will be coming out right here, and then you have your probe on the outside here to detect it, what they call a detecting element. This is actually what your probe is. This threaded device right here is going to be threading into the pipe. Usually it threads into the pipe where your medium is going to be, and then is stuck in so much inches so you can get an accurate flow temperature. Now this is where I want to stop and tell you about the reactor coolant system. In the reactor coolant system, we have a large pipe that comes out of the reactor. It's very, very large, approximately, what was that, 28 inches. That's pretty big for a hot energy level water coming out of the reactor coolant, out of the reactor vessel. And we have 3 thermocouples in that pipe. We have one that is, each one of them is approximately, was it 270 degrees? It's a Y shape. You have 3 of them. And what has been so interesting is that each one of the thermocouples measures a different temperature. And how can that be if they're in the same location on the pipe, so many feet from the reactor vessel, with their probe stuck in approximately 2 to 3 inches in? And all 3 are at the very same location, and all 3 are measuring different temperatures. How can that be? The first thing you would think of is, wow, I got 3 thermocouples and they need to be changed out. They are reading incorrect readings, but that's not the case. They've been pulled, they've been tested, and they all are operating as they should. They're calibrated correctly. What it is the unique property that comes out of the reactor vessel is that there is a laminar flow going through the pipe, and that laminar flow has different temperatures based on different locations within the pipe itself. The water, the heated water, doesn't actually start mixing till it gets over to the steam generator, which is pretty interesting. So when you're in the control room, you're going to see the monitors for these 3 thermocouples, and each one of them in that circular pattern is going to have a different temperature, but they're going to range fairly close. That's why we have what's called T average. If you were reading through your reactor coolant system manual, oops, that was NUC 120, sorry. In the reactor coolant system manual, it states that you have what's called a T average. T average is approximately 575 degrees Fahrenheit, and that is an average of all three of those thermocouples and what they're reading during normal operations. So that's pretty interesting there. Okay, moving on to the next section. Okay, before I move further, I want you to look right down here at the basic thermocouple instrumentation diagram. Notice over here it says the sensing junction. That's where the wires are connected together. Then you have your separate wires. In this particular case is aluminum and chromel wire, and they're coming out. Notice that the reference junction is where we connect up our metering. But I want you to notice normally our metering has a copper wire. We have just connected dissimilar metal to other dissimilar metals. And because they're dissimilar, this can create a different electrical current based on voltage than these will do. And so that's the problem right here at this reference junction, that we have copper wire intersecting with aluminum and chromel wire. And so we have to take care of this problem because our meter is going to be measuring the difference in potential here. And we want that measurement to respond to this temperature change here and not necessarily the copper. So let's turn to the next page. And they're going to talk about different ways and operation of how this thermocouple operation is created. So number one, the amount of current that is created due to the dissimilar metal. Whoops, let me get rid of that. It's right here. The characteristics of the two metals, we already looked at that. The temperature difference between the measurement and the reference junction. Notice measurement junction is the same thing as the sensing junction. It's located right here. That is that's located in the probe and put into your measuring fluid, whatever it might be. And then connecting it directly over to your reference junction. They call it cold junction. By doing this, you're able to have the two dissimilar metals connected to either side, which number one will help in maintaining the polarity or the voltage between the two dissimilar metals by having them connected both on the reference side and the measuring side. In that particular case, then we put the voltmeter in between. Now by connecting both sides, T1 versus T2, and then putting the copper, which is our third dissimilar metal, if you remember I talked about that, the copper, the third dissimilar metal, then these two junction points will therefore cause an equalization or a balance between the two, and therefore they will give an equal and opposite polarity, and therefore will not be changed by the usage of this copper here. It's a pretty neat invention on how to resolve this property characteristic based on adding copper to the voltmeter. Otherwise, the voltmeter is going to have to have this sensing metal or that sensing metal, and therefore would not based on the way a voltmeter is constructed inside, wouldn't give you the correct measurement of the volts being produced by the temperature difference between these two metals. Okay, that is better summarized over here on a figure 2-11, where it's talking again about the temperature of the two different types of metal or three types of metal. But the other thing is that if we connect this side to this side, then obviously 400 degrees here is going to travel through this wire. That's going to be 400 degrees over there. Well, if you have the same temperature on both sides, then you can't get a voltage difference between the two wires. So what we have come up with is what's called the junction box thermostat. The junction box thermostat normally keeps the reference temperature over here at a constant temperature. They show it as 50 degrees Celsius, which is great, a large difference between 400 degrees Celsius. If you're able to maintain this junction voltage temperature at the same temperature, then you can measure just the difference in temperature of these two metal devices and therefore get you a correct reading on your voltmeter. So there you go. The standard connection of a thermocouple is is this diagram here, figure 2-8. Then moving back down, they determine by adding or joining the measuring device, which is already joined anyway, with the reference junction, which is the location of your metering, you can balance out the difference in potential, which is shown here, and then putting your voltmeter in parallel, then the copper that's connected to the voltmeter won't have a big difference or differential voltage between the metals. And then the last thing is by putting some kind of thermostat or temperature regulation within your junction box so that your reference temperature is always maintained at one time. Now once you look at this junction box, they say they maintain it at 50 degrees Celsius. As you can see, what happens if your ambient temperature in the control room or in your auxiliary building and or your turbine building? What if the ambient temperature is not 50 degrees anymore? What if it now is 35 degrees Celsius or even 25 degrees Celsius? So you can see that ambient temperature might make a difference here based on your junction box trying to maintain it at 50 degrees Celsius. Second thing is, what happens if you have a high humidity? On this junction box, it's made out of metal, and if you have a lot of condensation on the box itself, you can see where it could lower the box just based on condensation, and therefore reduce your junction box reference temperature, which therefore would change the difference in your voltmeter reference, and therefore give you an inaccurate reading. So that's why the environmental concerns are appreciated with these measuring these thermometer detecting devices, because of the ambient temperature and or the humidity, which is your environmental controls. Okay, this gives you some a readout based on manufacturer specs as to what the temperature is of the two dissimilar metals and the voltage that is output. Obviously, if you know that as you increase in your temperature, you can see where your voltage changes, and notice that that's in millivolts. And so you remember, you got to have a large differential in your millivolts so your equipment can make the detection as to what the temperature is. If the millivolt number is very, very small in comparison to the temperature change of the dissimilar metals, then we'd have to put some kind of gain, operational amplifiers, things like that, to increase the value so that our sensing equipment can actually read it. Okay, the advantage of the thermocouple, it's fast response. It changes in temperature due to the thinness of the sensing wires. Also, that's only give one advantage. How about this? Disadvantages include, it requires compensation for nonlinear voltage signal. That is due to temperature changes, your indication, your reference temperature, so on and so forth. It's prone to erroneous errors to the changes in reference junction temperature. Remember, that was over here where your metering was connected to. And then we haven't even gotten to RTDs, but they say it is less accurate than an RTD, where RTD was a resistance thermodetector. Well, that concludes today's information concerning the thermal detectors, temperature sensors. In review, we had looked at a number of different of those detectors, and one of those being the all-known thermometer, including the boron spiral tube, in addition to the bimetal detectors that has the two different types of metals, and then we investigated the thermocouple. So for today, what I need you to do is go back and read through this material, go ahead and make sure you have your highlights correct, and therefore after that, you need to go down to the summary and then try to pick up on each one of the sample questions at the very end of the book, or end of your chapter, excuse me. Go ahead and work through those. I'm going to place on your blackboard for you a small little quiz based on the information we just covered today. So I want you to make sure you know that. Now on that quiz, I'm going to give you approximately 2, and if I feel real generous, 3 attempts to do that quiz. And also I will give you additional information for you to complete by Thursday. And what I'm going to do on that one is I'm going to have an additional quiz on Thursday, which you can do on home. It's not, you won't be doing it in class, you'll be doing it at home, and that'll be an unlimited attempts, and I'll give instructions on how to do that on Blackboard. So make sure you check your Blackboard this week. Make sure you do your discussion questions. Make sure you go through and check out the quizzes that I'll have on Blackboard under the quiz folder, and so that you'll be ready to go. All right? The next thing we're going to investigate is Lab 6 and get ready for lab.